Hey everyone, welcome back to Collapsed Latents, This Week in AI. I'm your host, and this week, we're not just tracking progress, we're dissecting the quiet revolutions that are redefining what's possible in artificial intelligence. From the hidden cost of flexibility in language models, to the dangerous illusion of personalization, robots learning from your point of view, a new benchmark that finally makes AI actually hear speech, and a breakthrough in steering AI with sparse, interpretable vectors that don't just work, they make sense. These aren't incremental updates. They're paradigm shifts. And they all point to a single, emerging truth. The future of AI isn't about more complexity, it's about deeper clarity. So grab your coffee, settle in, and let's dive into the 5 papers that are quietly reshaping the landscape, one elegant insight at a time. Paper 1, The Flexibility Trap, Why Less Order Means More Reasoning. First up, a paper from Tsinghua University and Alibaba Group that flips a core assumption in diffusion language models on its head. The conventional wisdom. More flexibility equals better reasoning. After all, diffusion models can generate text in any order. Skip ahead, fill in the easy parts first. Sounds like a superpower, right? But this paper, The Flexibility Trap, Why Arbitrary Order Limits Reasoning in Diffusion Language Models, delivers a brutal counterpoint. No. In fact, it's the opposite. Because real reasoning isn't smooth. It's punctuated by forking points, moments like therefore, since, however, where the model must choose between multiple logical branches. In autoregressive decoding, left to right, the model must confront that uncertainty in real time. It explores multiple paths. It preserves the solution space. But in arbitrary order decoding, the model avoids the hard part. It fills in the low-entropy, grammatically safe parts first, the parts that don't require judgment. Then when it finally returns to the fork, the context is already baked in. It's not choosing a path, it's just picking the connector that fits its pre-made conclusion. This is entropy degradation, a premature collapse of reasoning potential. The model never truly thinks. It just converges. So how do we fix it? The authors propose just GRPO, a radical idea. Train the diffusion model autoregressively, using stable, efficient group relative policy optimization. No complex reinforcement, learning over combinatorial trajectories. Just left-to-right training, the same way traditional LLMs are trained. And the results? 89.1% on GSM 8K. 45.1% on Math 500. Beating more complex diffusion-specific methods, without sacrificing parallel decoding at inference. Even under aggressive parallel sampling, just GRPO improves, gaining plus 25.5% on MBPP. The takeaway. Sometimes the best way forward isn't more freedom, it's more constraint. True reasoning isn't unlocked by arbitrary order. It's forged by forced confrontation with uncertainty. Flexibility isn't the answer. Discipline is. Paper 2, The Personalization Paradox. When AI remembers you, it forgets the truth. Next, a paper that exposes a dangerous blind spot in the rise of personalized AI. We've all seen it. ChatGPT remembers your preferences, Gemini knows your habits, Claude recalls your quirks. Personalization makes AI feel human. But at what cost? This paper reveals a new kind of hallucination. Personalization-induced hallucination, where the model confuses your history with objective truth. Imagine asking, which president's inauguration preceded the Civil War? A standard model says, Abraham Lincoln, 1861. But now, suppose you once said, I attended the Maundy Thursday service 4 days ago. The personalized model, now influenced by that detail, might reply, based on your chat history, you attended the service 4 days ago. Not just wrong. Completely off the rails. Why? Because personalization introduces a non-orthogonal signal into the model's latent space. It entangles with factual knowledge. We confirmed this with representation analysis. Hallucinated answers had significantly lower cosine similarity to truthful ones, proving it's not noise. It's a latent factual distortion. And the consequence is worse learning. In our simulation, students taught by personalized models scored 10.5% lower in factual accuracy. So how do we fix it? Enter FPPS, Factuality Preserving Personalized Steering, a lightweight, inference-time framework that detects and corrects hallucinations without sacrificing personalization. It works in 3 steps. 1. Identify the personalization-sensitive layer. 2. Probe it with a classifier that detects entanglement risk. 3. Steer the representation back to truth with a learned vector. 3 variants, hard, soft, and mixed steering. And the results? On our new benchmark, PFQA bench, FPPS boosts the balance of factuality and personalization by over 50%. FPPSM, the mixed approach, closes the learning gap, student accuracy improved by 7%. The insight: personalization should not be unconditional. It must be epistemically responsible. AI companions are powerful, but they must preserve truth, not just alignment. Because if we let AI learn from our quirks without truth checks, we risk building a future where memory replaces reality. Paper 3, Robots that learn from your point of view, the rise of egocentric intelligence. Now let's shift from language to action. What if your robot didn't need thousands of hours of training? Just a few minutes of you doing something in your kitchen. This isn't sci-fi. It's real, and it's powered by vision language action models trained on ego-centric video. First-person footage from GoPros, smart glasses, and wearables. Projects like Ego 4D, Epic Kitchens, and HD Epic have collected thousands of hours of messy, real-world behavior. Fumbling with jars, slipping spoons, doors that don't open. And now, AI is learning not just what to do, but why. The key. Action diffusion. Repurposing image diffusion models not to generate pictures, but to generate actions. Start with random, chaotic movements. Denoise them step by step, refining into a smooth, correct sequence. It's not copying. It's reasoning through possibilities. Models like diffusion policy, CogAct, and DexGrasp VLA generate flexible, robust behaviors, adjusting grip, recovering from slips, generalizing across tasks. But it's not just hands. Models like RDT1B and HRDT teach robots to use both hands, coordinate their torso, even walk, as a unified, embodied behavior. They learn affordances, not just what an object is, but how to interact with it, where to grasp, how much force when it might be slippery. And they're powered by chain-of-thought prompting, forcing the AI to explain its decisions, just like we do. The best part? Open weights, open data. Projects like OpenMM Ego, Ego Mimic, and Emma are democratizing this, giving students, creators, and researchers the tools to build robots that learn from life, not labs. This isn't about factory robots anymore. This is about robots in our homes, our kitchens, our lives. The future isn't in factories. It's in the wild. And it's already here. Paper 4, PRiSM, the benchmark that makes AI actually hear speech. Next, a paper that finally answers a question we've ignored for too long. Does AI truly understand speech, or just memorize patterns? Enter PRiSM, the first open-source benchmark for phone recognition that measures not just what a model transcribes, but how well it hears. Traditional benchmarks only care about transcription accuracy. But that's like judging a chef by the final dish, ignoring how they taste the ingredients. PRiSM fixes this with intrinsic plus extrinsic evaluation. Intrinsic uses phonetic feature error rate, PFER, a metric that computes edit distance over articulatory features like voicing and place of articulation. So if a model says cool instead of cool, PRiSM knows it's not just wrong, it's missing the voicing shift. Extrinsic, 2 probes. Transcript probe uses the model's own phonetic output to predict dysarthria, language, or dialect. Representation probe uses the model's internal features directly, bypassing transcription. The results? Eye-opening. Encoder CTC models like ZIPA-CTC and POWSM-CTC outperformed even top LALMs like Gemini 2.5 Flash and QN3 Omni-Instruct. LALMs showed strong geographic bias. QN predicted New Delhi for every Hindi dialect input. Zero-shot phone inventory induction. POWSM-CTC won because it produces precise, low-entropy transcriptions. And here's the kicker. The transcript probe outperformed the representation probe in geolocation because dialects differ in sequence, not just features. The lesson? You can't judge a model's phonetic understanding by transcription alone. And you can't trust pooled representations. They erase critical structure. PRiSM isn't just a benchmark. It's a wake-up call. Because if we want AI that helps diagnose speech disorders, teach pronunciation, or support multilingual inclusion, we need models that truly hear. Real progress isn't about bigger models, it's about deeper understanding. Paper 5, YaPO, the sparse, interpretable steering revolution. And finally, the most elegant solution to one of AI's biggest control problems. How do we steer large language models with precision, stability, and interpretability? Traditional methods. RLHF is expensive. Fine-tuning is slow. Prompt engineering is brittle. Enter activation steering, injecting vectors into hidden states at inference time. But early methods like CAA were noisy. BiPo was powerful, but dense vectors led to entanglement. A single neuron could encode multiple concepts, so steering one behavior broke another. Enter YaPO, yet another policy optimization, a breakthrough that operates in the sparse space of a sparse autoencoder, SAE. Here's the magic. SAEs decompose activations into approximately monosemantic features, each a single, interpretable concept. YaPO learns sparse steering vectors in the space, each dimension tied to a clean idea. It optimizes via a DPO-style objective, maximizing preferred responses, minimizing dispreferred ones, but in the sparse code space. The results? 10x faster convergence. YaPO hits 0. One loss in 150 steps versus BiPo's 600. Smooth, stable scaling, no sudden collapse at high steering strength. Full interpretability, you can inspect the vector. Ah, this is the formal greeting feature. And in cultural alignment, a domain where fine-grained distinctions matter, YaPO closes the localization gap better than any baseline, with highest robust cultural accuracy and lowest PNLG. Best of all, it doesn't hurt general knowledge. MMLU scores stay rock solid. YaPO isn't just a tool, it's a new paradigm. By operating in a disentangled space, we get alignment that's not just effective, but understandable, shareable, and composable. Imagine fine-tuning a model's behavior across hundreds of cultural, ethical, or domain-specific dimensions, not by retraining, but by combining sparse, interpretable vectors. This is the future of controllable AI. So what's the big picture this week? We've seen that flexibility can be a trap, personalization can distort truth. Robots can learn from your perspective, AI must truly hear, and steering must be sparse, interpretable, and stable. But beneath it all, a single, unifying insight. The most powerful AI isn't built from complexity. It's built from clarity. It's not about more features, more data, more parameters. It's about better design. About constraints that force insight. About alignment that preserves truth. About tools that are not just powerful, but understandable. This is the shift we've been waiting for. AI isn't just getting smarter. It's getting wiser. If you enjoyed this deep dive, hit like, subscribe, and ring the bell because next week, we're tackling embodied reasoning in humanoid robots and how they're learning to fall, recover, and keep going. Until then, keep questioning. Keep exploring. And remember, the future of AI isn't just in the models. It's in the mindset behind them. See you next time.